we want to pick up in the second part of Chapter 4 exactly where we left off, and that is talking about precipitation reactions and how we write out the equations for those. The question will come up, how do we know if a compound is going to be soluble or insoluble? And we're going to focus on ionic compounds for this part of the course. But what we'll notice is that hydroxide compounds are not soluble in water except for group 1A hydroxides like sodium hydroxide, lithium hydroxide, potassium hydroxide, and 3 of the group 2A hydroxides, calcium, strontium, and barium hydroxide. Those are soluble in water, at least to a noticeable degree, whereas other hydroxide compounds like iron hydroxide, aluminum hydroxide, and so on are not significantly soluble in water. Sulfides tend not to be soluble in water. And again, the exception to that rule are the first column metals, a few of the second column metals, and NH4 sulfide, ammonium sulfide. Carbonates are not soluble in water except for the first column metals and ammonium ions, so ammonium carbonate or potassium carbonate and so on are soluble in water. Phosphates are not significantly soluble in water with those same exceptions. Column 1A, lithium, potassium, sodium, and NH4. Now what that means is that nitrates are soluble in water. Perchlorates are soluble in water. For the most part, chlorides are soluble in water. An exception in the area of chlorides would be silver, lead, or mercury. Similarly with sulfates. Sulfates are for the most part soluble in water with those few exceptions. Fluorides, bromides, and so on soluble in water except for silver, lead, and mercury. So a combination of a non-soluble cation from one solution and a non-soluble anion from another solution will make a precipitate. What we have going on here is lead nitrate being mixed with sodium iodide like we discussed earlier. Lead nitrate is soluble because nitrates are always soluble. Sodium iodide is soluble because sodium compounds are always soluble. But lead iodide is not soluble because we said silver, lead, and mercury halides are not soluble. So again, like we said earlier, if we want to write the molecular equation for that reaction, we have that written right here. And then we can write the ionic equation separating aqueous compounds into ions. And then, but leaving the solids as whole formula units. And then we can eliminate the spectator ions and write the net ionic equation. So let's try a sample question. You guys can pause the video and write this down. Try it out on your own. Look things up on the internet if you need to. We'll talk about this in class. Does a precipitate form when sodium chloride is mixed with silver nitrate solution? If so, write the net ionic equation. And remember that the formula for sodium chloride is NaCl. So we're going to have ions Na and Cl, Na plus and Cl minus. And then silver nitrate would break down to Ag plus and NO3 minus. So try that one out. See if you think there will be a precipitate based on what we've said and what that precipitate will look like. Now I want to shift gears a little bit from solubility and precipitation reactions, talk about acids and bases. The historical model for acids and bases are what we would call an acid. This was developed by a scientist named Arrhenius. What we call an acid was anything that could supply H plus when dissolved in water. And we still use that definition for the most part today. The old definition of a base was anything that could supply hydroxide ions when dissolved in water. But what we found is that some compounds that didn't have hydroxide behaved like bases. They caused the pH to go up. And the reason for that is that that hydroxide ion consumes hydrogen ion to make water, and some other compounds like ammonia consume hydrogen ions as well, and they function as bases as well. So the Bronsted-Lowry, the newer definition of acid, is very similar to Arrhenius's, but the definition that we use now for bases, Bronsted-Lowry base, is expanded to say anything that consumes hydrogen ion. The other trick to this, and this has to do with this picture down here, we call the ion that acids cause or give in solution H+, because we think of HCl, for example, as breaking apart to make H+ and Cl-. But in reality, that's not what happens. In solution, we don't see hydrogen ions by themselves. The hydrogen ions get stuck to a water molecule, and we see H3O+, as we've pictured here, in solution instead of H+. So some books will call it H+, for historical reasons, even though we know that this is the case. Other books have switched and started calling the acid ion primarily H3O+. Not all hydrogen atoms on all molecules are acidic. For example, this is a drawing representation of acetic acid, the acid that's active in vinegar. And that molecule has 4 hydrogen atoms on it. And when it dissolves in water, this particular bond here, we represent bonds that are made of electrons with these lines. The oxygen is hogging these electrons. So the hydrogen's kind of out here by itself. That makes it easier for water to interact with it. And so when acetic acid dissolves, some of these hydrogens that are attached to the oxygen get broken off by water molecules, and it behaves as an acid. These bonds are not that way. The electrons causing these bonds are very evenly shared between the carbon and the hydrogen. And so water doesn't interact particularly well with these hydrogens. They stay stuck to the carbon. They're not acidic. So only one of the hydrogens on acetic acid behaves in an acidic manner. When we're naming acids, we talked earlier about naming ionic compounds and covalent compounds. The name of an acid depends on what ion the acid's made from. For example, HNO2 is an acid that is based off of H+ and nitrite ion. When an ion name ends in "ite," the acid of that ion is called nitrous acid. The acid of that ion is called, it has an OUS in its name. Nitrate, ATE ending on the anion, we call the acid of that one nitric acid. So we get an IC ending out of the 8. So phosphate ion gives us phosphoric acid. Sulfite ion gives us sulfurous, ate-ic for sulfate and sulfuric. Hypochlorite would be hypochlorous acid then. And chlorite ion would give us chlorous acid. Chlorate would give us chloric. Perchlorate would give us perchloric. When the anion that makes the acid has an IDE ending, like HCl has, chloride ion on it, then and only then do we use the hydro prefix on the name of the acid. Hydrochloric acid. HBr is hydrobromic acid. Now, let's try out a problem, and you can again pause the video and write this down. I'll try to give you some hints as I explain it. But the question is, how many milliliters of 0.125 molar sodium bicarbonate solution are needed to neutralize 18 milliliters of 0.1 molar HCl? So the way I would start this out is with the 18 milliliters, 18.0 milliliters. And we have of here. Of in grade school word problems, just like in college word problems, means multiplication. So times 0.100. Now I wouldn't write a capital M as my unit. I'd write moles per liter as my unit. And what you're going to realize then is that if you multiply milliliters by moles per liter, your units don't cancel. But you can use a conversion factor, 1,000 milliliters is a liter, to get both the liters and the milliliter to cancel. And then you'll be left with units of moles. Then you can multiply by 1 over this molarity. So 1 liter is 0.125 moles of sodium hydrogen carbonate. And convert to milliliters, and you'll have the answer to the question. So we'll work that one out together in class next time we meet. The final reaction type that we want to talk about, and we'll spend the rest of this video and the next video, third video for this chapter, talking about this type of reaction that we called earlier a redox reaction or an oxidation reduction. What's happening in a redox reaction is some element is being oxidized. It is giving up control of one or more electrons. And some other element is being reduced. It's taking electrons. Now the reason that sounds counterintuitive. The reason we call it reduction when something is taking electrons is because its charge goes down. If something takes an electron, it can go from 2 plus to 1 plus. Its charge got reduced. It can go from 1 plus to neutral, or from neutral to 1 minus. But oxidation is an increase in the charge by losing an electron, since electrons have negative charge. So the way that we'll keep track of redox reactions so that we can tell what is happening is by looking at the oxidation number. And so we've got some rules to talk about what the oxidation number is for a particular element. One of those rules is that an element in its natural state is going to have oxidation number 0. So Na, no charge, not part of a compound, oxidation number on the sodium is 0. But if something has a charge, if an element has a charge like these particular cations and anions do, then the oxidation number is whatever the charge is. Sodium plus, got a +1 oxidation number. Calcium 2 plus, it's got a +2 oxidation number. Typically we write charges with the number first and the sign second, and then we write oxidation numbers with the sign first and the number second. That's the convention that's used most often. Now, if we're looking at a molecule or a polyatomic ion, more often than not, the oxidation number that we're going to use for that particular atom in that molecule is the same as it would have had as an ion. And the most common ones of these would be fluoride is always -1. Oxygen is always -2 when it's not bonded to fluorine. Hydrogen is always +1 when it's not bonded to a metal. When hydrogen is bonded directly to a metal, it's -1. Another exception to that, when oxygens are bonded directly to each other in a peroxide ion, the oxygens are behaving like -1 instead of -2. Typically, you can figure out all other oxidation numbers in a compound or in a species using that set of rules. And here's that exception we just talked about, where oxygen is -1 in a peroxide case. Now, chlorine is usually going to be -1, but notice here it is +1 because oxygen is -2 anytime it's not bonded to fluorine and not a peroxide. So some of these will have exceptions. Fluorine does not. Hydrogen and oxygen only have the exceptions that we talked about.